All right, we are at section 15.3, energy of a simple harmonic oscillator. So let's share the PowerPoint. We'll get started here. You're familiar with this uh, graphic here. When the block is displaced to the right of equilibrium, the force exerted by the spring acts to the left. When the block is at the equilibrium position, the force exerted by the spring is zero. And when the block is displaced to the left of equilibrium, the force exerted by the spring acts to the right. So the kinetic energy is 1/2 mv squared, which is, is the velocity is omega a sine omega t plus phi. So square that, you get that the kinetic energy is equal to 1/2 m omega squared a squared sine squared omega t plus phi. Now omega is equal to k over m. Omega squared is equal to k over m. If you recall, omega is equal to the square root of k over m. So omega squared is equal to k over m. If we substitute that in this equation, we'll get 1/2 k a squared sine squared omega t plus phi. Now the spring potential energy is 1/2 kx squared equals 1/2 k a squared cosine squared omega t plus phi. Now we just turned the kinetic energy equation into 1/2 k a squared sine squared omega t plus phi, because omega squared is equal to k over m. So they both have a 1/2 k a squared, so we can pull that out using the distributive property. And so the total energy, the kinetic energy plus the spring potential energy, is 1/2 k a squared sine squared omega t plus phi plus cosine squared omega t plus phi. Well, if you have sine squared theta plus cosine squared theta, that's always equal to 1. That's an identity. So that the total energy, K plus the kinetic energy plus the potential energy is the total energy is equal to 1/2 K a squared. All right, so this is what the 1/2 K a squared looks like, and you can see that there's that the sum of these always equals to this 1/2 K a squared. What is that? I forget what that one is displaying. Let's see. Variations. The energy is continuously being transformed between the potential energy stored in the spring and the kinetic energy of the block. And we've seen that with the Walter Fent demonstrations. Of course, that's a vertical oscillation, and so it goes from spring potential energy to kinetic energy to gravitational potential energy at the top of the spring. But there's always this transfer of potential energy and kinetic energy. And you can see here the total energy in red never disappears, and we swing between potential energy. When the spring is pulled, it's potential energy. It's all kinetic energy as it goes through the zero crossing. Then spring potential energy on the other side, and it just goes back and forth. So we could see that. We saw that with again, the Walter Fent demonstrations. Now we have 1/2 the total energy E is equal to the kinetic energy plus spring potential energy. So that's 1/2 mv squared plus 1/2 kx squared. That's equal to E. We just showed that was 1/2 k a squared. So if we solve for V, we get V squared, or we take the 1/2 kx squared to the other side. We have uh, 1/2 V squared equals to 1/2 Ka squared minus 1/2 Kx squared. So we can bring out, we divide both sides by M. Well, first of all, we can take the 1/2 off of everything. So we end up with V squared equals to K divided by M times A squared minus X squared. But if you recall, omega is equal to the square root of K over M. So V equals the square root of, or V equals omega times the square root of A squared minus X squared. And we can use this to find the position, find the velocity of any position. You can obtain the velocity of any position by an arbitrary position X by expressing the total energy of the system at some arbitrary position X. Now the harmonic oscillator it kind of models. You can see the parabolic well there for the potential energy times the radius of atomic structure. So there's a small potential for small displacements of equilibrium. You know, the atoms move about a small area. You can model them as springs, and the potential energy curve for this function approximates a parabola. It represents a potential energy function for a simple harmonic oscillator. So you can model the complex atomic binding forces as being due to the tiny springs, the little figure B there. Other examples are bungee jumping, playing a musical instrument, and viewing light emitted by a laser. Okay, and I think before we get into that next section, this ends 15.3.